Hey guys, this is going to start off our unit on forces and motions. We're going to start with Newton's 3 laws of motion. So a lot of people know what Newton's laws say, but we don't know what they mean. So that's what we're going to be working on this week. So just a quick overview of what the 3 motions are. And then we will go into each one more depth. So the first law is called the law of inertia. Basically, an object at rest is going to stay at rest. An object in motion will stay in motion unless acted on by an unbalanced force. Okay, that's the first law. The second law is just a formula, force equals mass times acceleration. You're going to be doing lots of practice with that one. And then the third law is for every action there's an equal and opposite reaction. So let's go into the first law of motion. Again, an object at rest will stay at rest. An object in motion will stay in motion at a constant velocity. That means going the same speed and in the same direction unless it's acted on by an unbalanced force. So that's why it's called the law of inertia. So inertia is the tendency of an object to resist changes. So if it's in motion, it wants to stay in motion. If it's at rest, it wants to stay at rest, just like those pumpkins over there. They're not going to move unless somebody puts a force on them, a push or a pull, to move them. Okay, if we look at this example of the golf ball, that golf ball wants to sit on that tee for forever and ever and ever. That's the law of inertia. But along comes the golf club and puts an unbalanced force, forcing that ball off the tee. Okay? If there was no gravity on Earth, that ball would keep going and going and going, and also if there was no friction. So the air creates wind resistance or air resistance, and that's a type of fluid friction. Those things make that ball stop. They make it fall to the ground, and the friction makes it stop. Okay? We just talked about that. So then why every day do we observe objects in motion slowing down and becoming motionless without an outside force? We just talked about that with the golf ball. One of them is gravity, the other one is friction. Okay, so on Earth we have lots of matter. Okay, the air is made up of matter, things you breathe. Remember, matter is anything that has mass and takes up space. So even though we can't see air, we can definitely feel it when it's blowing on our face. So it has matter and it takes up space. The other thing is friction, the unbalanced force that makes an object stop moving. If you roll a bowling ball, eventually that bowling ball is going to stop rolling because of friction. 4 main types. The first one is sliding friction. An example is ice skating. Okay. Another one is rolling friction. So anything that's rolling. A soccer ball has rolling friction after you kick it and it's rolling. Bowling ball has rolling friction. The other one is fluid friction. We talked about that. The air, it's air or liquid, so air or water resistance. If you're swimming, that's fluid friction. If you're running, you can feel that air on your face. That's fluid friction. That's air resistance. And the last one is static friction, and that one is the initial friction when you're moving an object. That one, guys, I'm sure you've experienced that one before when you're trying to move or push something really heavy. Like maybe you're moving your furniture around in your room and you try to get your dresser moving, and that initial push to move your dresser, it takes a lot more force. Once you get it going, you're like, hey, this isn't so bad, but that initial push is because the object has static friction and it doesn't want to move. So there's a little bit more friction when you first start moving something. Okay, if you want to do an experiment yourself, you can slide a book across the table and watch it slide to a rest position. The book is going to rest because of friction. Okay, again, because we're sliding it, it's sliding friction. That is going to make the book stop. If we were in outer space and you push that book, it's going to keep going and going and going. Just like the Earth revolves around the sun forever and ever, and we're going the same speed as we were 1,000,000 years ago. Because there's no friction, the Earth is not encountering any friction in outer space, so we just keep moving at the same velocity around the sun year after year after year. Okay? So that's what I was talking about with the Earth moving through space. If there's no force of friction, the book would continue to move with the same speed and direction forever. Okay? So here's Newton's first law. Again, an object in motion will stay in motion. An object at rest will stay at rest at a constant velocity unless acted on by an unbalanced force. So with this car, what's happening is the car is moving. So the car hits the wall, which is the unbalanced force, but that person in that car is moving at the same velocity. So even though the force was acted on the car, the force was not acted on by that person. He wasn't wearing a seatbelt. There was nothing to stop him. So he continues moving forward at that same velocity as that car was moving. And it says 80 kilometers per hour. So that car stops, that person is still moving 80 kilometers per hour, which is why when people aren't wearing their seatbelts and they get in an accident, they're found a long way from where the car got in the accident because they are thrown out of the car because they're still moving at that same speed. Okay, here's our second law. Force equals mass times acceleration. It's just a formula. You use this just like you do in math. You plug and play. You have the numbers, you plug them in, and you figure out the missing part of the formula. Okay, so the force of an object is equal to its mass and its acceleration. So the couple things that you have to know. When you're measuring the mass of something and you're trying to figure out a force, the mass has to be in kilograms. So if it's not in kilograms, you might have to do a little bit of converting to get it to kilograms. Acceleration is always measured in meters per second per second. Okay, and then if you have kilograms over meters per second, that's called a newton. Okay, 1 newton is equal to the force required to accelerate 1 kilogram 1 meter per second per second. Okay, so when we measure force, the units that we use is newtons. Okay, so here's the law in action. How much force is needed to accelerate a 1,400 kilogram car 2 meters per second per second? Our mass is in kilograms, and our acceleration is in meters per second per second. So the first thing we're going to do is write the formula. Here it is, force equals mass times acceleration. Then we're going to fill in the numbers. The mass is 1,400. The acceleration is 2 meters per second. So then we're going to solve for the unknown. 1,400 times 2 is 28 kilograms meters per second, which I told you before is a newton. So that is the unit for that. So we have 2,800 newtons is the force. Okay? Let's practice some more. Okay, so here's just a little table. It shows you what happens to your acceleration or your force depending on what is happening to your mass or your acceleration. So if we have our mass at 2 kilograms and our acceleration at 5 times 2 equals a net force of 10. We're going to keep our mass at 2 kilograms, so our mass is exactly the same, but we're going to double our acceleration. So because we're doubling our acceleration, we double our force. Okay? So now this one's a little bit different. It's giving us the force. We're missing a mass. It gives us acceleration. Our acceleration is 5. Our net force is 20. So 5 times what equals 20? We doubled our force. Our acceleration is the same as our first one, so that means we have to double our kilograms. 5 times 4 equals 20. Okay? And then here's this one. 10. Our net force is 10. Our mass in kilograms is 5. 5 times what equals 10? This should be 2 meters per second. And then this is the regular formula. Force equals mass times acceleration. So mass is 1, acceleration is 10. Our net force is 10. Okay? Okay, so something that we don't know, because we haven't talked about it, but what you need to know is that different masses, so anything with different weights, will accelerate to the earth at the same rate, but they're going to hit with different forces. So what we need to know is that if you drop two things at the same time, say you drop a hammer and a basketball, obviously that hammer weighs more than the basketball. The hammer and the basketball are going to hit the floor at the exact same time. But which one's going to hit with a greater force? The one that has the higher mass. Okay, so if you look at these two boulders right here, obviously this one weighs more than this tiny one right here. But if we drop those boulders, they're going to hit the ground at the same exact time. They're going to hit this ground at the same exact time. However, their force is going to be different. The force of this big boulder ends up being 98 newtons, and the force of this boulder ends up being 9.8 newtons. Okay? All right. That's what we need to know. And if we'll watch a short clip in class of they did this experiment in outer space. I think they dropped a feather and something else, which is they were trying to show that because there's no friction in space, because obviously here a feather is going to catch that air and there'll be air resistance as it floats down, but in space it doesn't do that. I think they dropped a hammer and a feather in outer space, and those two things hit the ground at the exact same time on the moon, and I'll show you guys that clip. It's pretty neat. Okay, so objects are going to accelerate at the exact same time. They are going to hit at the same time, but they're going to hit with a different force. Okay? All right, so we're going to check for some understanding. We're going to go through these together. I want you to write down the answers in your notebook. So it says, what acceleration will result when a 12 Newton net force is applied to a 3 kilogram object or a 6 kilogram object? So we'll start up here, F equals M times A, and we'll plug and play. We have the force, and we have the mass, 3 kilograms times A. So for a 3 kilogram object, 3 times what equals 12? That one is going to be 4 meters per second per second. That's our acceleration. If it's a 6 kilogram object, again we have 12 equals 6 times our acceleration. 6 times what equals 12? That is going to be 2. Okay, so for a 3 kilogram object, it's 4. For a 6 kilogram object, our acceleration is 2. Okay? Alright, a net force of 16 newtons causes a mass to accelerate at a rate of 4 meters per second. Determine the mass. Okay, so we are given our force, 16 equals our accelerate. We don't know our mass, so we're going to write an M times our acceleration is 4. So 4 times what equals 16? That answer is going to be M equals 4. 4 times 4 is 16. So these are obviously super easy. You can do these in your head. All right, force equals mass times acceleration. It says how much force is needed to accelerate a 66 kilogram skier. That's our mass. Times our acceleration, 1 meter per second per second. 66 times 1, F equals 66. And our unit, guys, remember when we're measuring force is Newton, 66 newtons. Okay, and then the last one, force equals, what is the force on a 1,000 kilogram elevator that is falling free at 9.8 meters per second? Acceleration is 9.8. So force equals 9,800 newtons. We're going to move that over 1, 2, 3. 1, 2, 3 places. 1,000 times 9.8 is 9,800. Okay? All right, so that's your first part. And here are all the answers if you didn't get those down while I was going over it. Okay? So here's where we define the word force. Force is a push or pull that causes a change in motion. So gravity is a force between objects. Okay? Electricity, again, static electricity. Electricity is your force of electrons. Magnetism is the force of a field. And then friction is force opposing motion. And we talked about that one already when we had the different types of sliding friction, rolling friction, fluid friction, and static friction. Okay? A force is a push or a pull. So anytime you push or pull something, you are exerting a force. Okay, our third law, for every action there's an equal and opposite reaction. You do something, something happens in return for everything you do. Okay, so according to Newton, whenever objects A and B interact with each other, they exert forces upon each other. When you sit in a chair, your body exerts a downward force on the chair. The chair exerts an upward force on you. That force is equal. That's why when you sit down, you don't move. If the force of you was greater than the chair, then when you sat down, you would fall to the ground and the chair would break. Okay? If the force of the chair was greater on you than you were on it, then when you sat on the chair, you would be going upwards. Okay? So there's two forces resulting from this interaction, a force on the chair, a force on your body. These two forces are called action and reaction forces. Action and reaction. Okay, for every action there's an equal and opposite reaction. Okay, in nature. Okay, so think about this, guys. There's a lot of things that happen in nature that explain Newton's third law. So we're obviously looking at some fish here. The fish are going to use its fins to push the water backwards. That's the action. The reaction is that the fish goes forward. Okay? The size of the force on the water equals the size of the force on the fish. That's why the fish propels forward. Same thing happens with birds. Birds push down on the air. The bird goes up in the air. So the action is pushing down. The reaction is the bird goes up. Okay? It's the one we just talked about. Here's some more birds. Good times. Okay, here's action-reaction with baseball. So the baseball forces the bat to the left, which is the action. The bat forces the ball to the right, which is the reaction. So hitting the ball. So the bat comes... The baseball forces the bat to the left, and the bat forces the ball to the right. So when you hit a car on the way to school, a car is equipped with wheels which spin backwards. As the wheels spin backwards, they grip the road and push the road backwards so the car goes forward. Okay, a jet, the same thing. Okay, so the hot gases explode and push the bottom of the rocket, and then the rocket goes upward. And that is it. Those are our Newton's 3 laws of motion.